Tonight, on Space Science, the danger is not only the heat itself. Across the United States, this heat wave is changing into something far more serious as hot air, humidity, smoke, sleepless nights, and overheated cities begin to push the human body closer to its limits. What may look like ordinary summer weather is becoming a slow-moving threat that reaches from the atmosphere above the country to the skin, the lungs, the heart, and the mind. If this kind of deep, science-based story is worth exploring, please like the video, subscribe to Space Science, and stay with the channel as this story begins. Above the United States, the first region is the broad sweep of the lower atmosphere, spread across plains, mountains, deserts, coasts, and river valleys. At this scale, the land below appears varied, but the air above begins to behave as one connected system. A vast area of high pressure settles over part of the continent and lingers. High pressure means that air is sinking rather than rising. As it sinks, it is compressed by the greater pressure below, and compression warms it. The warming does not come from fire or from any special source of heat hidden in the sky. It comes from the simple physics of air that is pressed into a smaller space. When this process continues over many days, a broad dome of warm, stable air forms over the country. Meteorologists often call this a heat dome, because the air mass acts like a lid. It does not trap heat in the same way as glass over a garden bed, but it does create a pattern that discourages clouds, weakens vertical mixing, and allows sunlight to pour down day after day. In this outer atmospheric region, sunlight is the steady driver. Summer brings long hours of incoming solar energy. Under clear skies, the ground absorbs much of that energy and warms quickly. Soil, rock, pavement, and vegetation all take in sunlight in different ways. But at the continental scale, their combined effect is simple. The surface heats the air just above it, and that warmth builds during the day. If winds are weak and the same pressure pattern remains in place, the warmed air is not easily replaced by cooler air from elsewhere. The pattern becomes persistent. Persistence matters as much as intensity. A very hot afternoon can be dangerous, but a long sequence of hot afternoons under the same stable sky shifts the event into something more serious. The atmosphere is no longer delivering a brief pulse of heat. It is maintaining a background state in which heat accumulates across the land. The high-pressure system also influences the jet stream, the fast river of air that moves from west to east high above the surface. The jet stream rarely travels in a straight line. It bends northward and southward in large waves. When one of those waves arches strongly northward over a region, a ridge forms. A ridge is an elongated zone of higher pressure aloft. Under such a ridge, air tends to sink. Skies often remain clearer, and storms are less frequent. The shape and position of the ridge help determine where the greatest heat settles. Sometimes it expands, sometimes it shifts only slowly. When it stalls, the ground beneath it receives repeated days of strong sunshine and limited relief. The national weather pattern then begins to resemble a machine running in one mode without interruption. From far above, the first signs of danger do not always look dramatic. There is no single wall of cloud, no violent rotating system, no obvious edge that marks the event. Instead, there is steadiness. The ridge holds. The skies remain open. The air mass ages in place. Each clear morning allows another day of rapid warming. Each hot evening leaves behind energy stored in the ground and in the built environment. The event deepens because the atmosphere is not resetting. It is preserving the conditions that make heat spread and persist. This persistence depends on the balance between incoming and outgoing energy. During the day, the surface gains energy from the sun. At night, the surface loses energy by releasing heat upward as infrared radiation. Clouds can slow that loss by absorbing and re-emitting some of the outgoing energy. Dry, clear air can allow more heat to escape. Wind can also help mix surface air with air from above, sometimes easing the build-up near the ground. But under a stable high-pressure system, these balancing processes are often limited. Even where nights bring some cooling, the daytime heating begins again before the land and air have fully recovered. Over several days, the effect is cumulative. The atmosphere above the country becomes not simply hot, but primed to remain hot. Large-scale heat events also interact with the shape of the continent. Mountain ranges steer the flow of air. Deserts heat rapidly under strong sunlight. Plains allow air masses to spread broadly with fewer topographic barriers. Coastal areas may gain some moderation from nearby water, yet even that influence weakens when the regional pattern is strong enough. A continental heat wave is never perfectly uniform, but the outer atmospheric control can still dominate very different landscapes at once. That is one reason such events strain forecasting, infrastructure, and health systems over wide areas. Many places that usually differ from one another begin to share the same broad atmospheric burden. The warming climate adds another layer to this large-scale picture. Scientific observations show that average temperatures have risen, and this changes the baseline from which heat events begin. A heat dome forming in a warmer world tends to produce higher temperatures than a similar pattern might once have produced. The exact contribution of climate change to any single event can be assessed through careful attribution studies, and those studies vary by region and event. But the broader conclusion is well established. As the climate warms, heat waves become more frequent, longer lasting, and more likely to reach extreme levels. The atmosphere does not need a completely new pattern to become more dangerous. An existing pattern can deliver greater heat simply because the background conditions are warmer than they used to be. Within this first region, the key transformation is subtle but fundamental. What begins as a broad pressure pattern becomes a sustained alteration of daily life below. The outer sky sets the rules. It decides whether clouds grow or fail to grow, whether cooler air can move in or is held back, whether yesterday's warmth is erased or carried into tomorrow. In a dangerous heat event, the answer is often the same across many consecutive days. The atmosphere chooses repetition. Sinking air continues to warm, the ridge remains in place, the surface continues to absorb sunlight. The nation below lives under a sky that appears calm, but calm is not the same as safe. This is why a heat wave can shift from severe to far more dangerous without any need for thunder, flame, or violent wind. The change happens through duration, scale, and stability. The air above the United States settles into a pattern that supports heat and resists interruption. In that broad outer layer, the event gains its structure. The heat is no longer just a matter of one afternoon reaching a high number on a thermometer. It becomes an atmospheric regime, spread across a continent-sized landscape, quietly holding its position while the land below warms beneath it again and again. Beneath the broad high-pressure pattern, the next region is the moving body of air itself, the great mass that spreads across states and carries heat from one place into another. Air is never only temperature, it is also moisture, pressure, density, and motion. In this second region, the danger grows because hot air and moist air often arrive together. They do not always form in the same place, and they do not always move by the same path. But when they meet over inhabited land, the character of the heat changes. A dry heat can be intense. But humid heat places a different burden on the human body and on the environment. The body depends on evaporation to cool itself. When the air already holds a great deal of water vapor, evaporation becomes less efficient. The heat then stops being only an external condition and becomes a direct challenge to the body's ability to maintain balance. A large air mass develops its properties through contact with the surface below and through its history of movement. Air that spends time above very warm land becomes hot. Air that moves northward from warm ocean waters or from wet ground can gain moisture. In the United States, especially during summer, the Gulf of Mexico often serves as a powerful source of humidity for the central and eastern parts of the country. Winds circulating around a high-pressure system can pull this moisture inland. Over plains, river valleys, cropland, wetlands, and cities, the air continues to change. Water evaporates from soils, lakes, and reservoirs. Plants release water vapor through their leaves, a process called transpiration. Together, evaporation from land and transpiration from plants are often described as evapotranspiration. The word is technical, but the meaning is simple. Water moves from the surface into the air. When this happens beneath strong summer heat, the atmosphere near the ground can become heavy with warmth and moisture at the same time. The measure that people feel most directly is often not the air temperature alone, but the combination of temperature and humidity. When air is dry, sweat on the skin can evaporate more readily. Evaporation uses energy, and that energy comes from heat at the skin surface, helping the body cool. When air is humid, the gradient between wet skin and the surrounding atmosphere is reduced. Sweat may still form, sometimes in large amounts, but it does not evaporate as effectively. Instead, it can remain on the skin or soak clothing. The body works hard, yet the benefit is smaller. In scientific terms, the cooling efficiency declines. In ordinary terms, the air begins to feel thick, oppressive, and resistant to relief. This change is why a region with only moderately lower air temperatures can still become more dangerous than a hotter but drier region. The atmosphere surrounding the body matters because heat stress depends on how readily the body can shed internal warmth. Meteorologists and health agencies use several ways to estimate this combined burden, including indices that account for both heat and humidity. These values are useful, but the deeper physical truth is simpler than any index. The body's a warm organism that must keep its internal temperature within a narrow range. It loses heat through radiation, through contact with cooler surroundings, through breathing, and especially through evaporation of sweat. Humid air weakens one of the most important of these paths. A hot, moist air mass therefore turns ordinary summer activity into a much greater physiological strain. At the regional scale, this moist heat is shaped by circulation. Air does not stand still beneath the high-pressure system. It curves around the pressure field, sometimes drawing hot air from desert or interior land and combining it with moisture from the south and southeast. The exact track changes from one event to another, but the result can be similar across many cases. The land heats strongly by day. Southerly flow feeds moisture northward. The near-surface layer becomes increasingly warm and humid. This process can be self-reinforcing in agricultural regions. Moist soils and dense summer vegetation supply additional water vapor to the air. Irrigated land may also enhance humidity. As a result, the atmosphere near the surface can become not only hot from solar heating, but also saturated with the byproducts of the landscape's own water cycle. There is another way in which moisture changes the character of a heat wave. Water vapor is itself a greenhouse gas. In the lower atmosphere, it absorbs and re-emits infrared radiation. its amount varies naturally and rapidly, unlike carbon dioxide, which is more evenly mixed and longer lived. But during a humid heat event, abundant water vapor can reduce how quickly heat escapes from the surface and the near-surface air, especially during the evening and night. The main driver of the event remains the large pressure pattern and the intense daytime heating, but humidity can help the atmosphere hold on to warmth. This is one reason the air mass can feel so persistent and tiring. It is not only hot in daylight, it also resists cooling after sunset. The moist air mass also changes the texture of the sky. A person on the ground may notice a pale or hazy appearance, even without thick cloud cover. Some of this haze can come from pollution or smoke, but some comes from moisture itself, as tiny suspended droplets and humid air scatter light differently from dry air. The visual effect is gentle, but it signals a substantial physical shift. The atmosphere has become more crowded with water molecules, more capable of slowing evaporation and more likely to preserve heat close to the surface. Under these conditions, a hot wind no longer feels cleansing or dry. It can feel like air already used once, air that offers little exchange. In this second region, it becomes clear that danger is not carried by temperature alone. Two places can share the same thermometer reading and impose very different levels of stress. The hot, dry air of a desert afternoon affects the body in one way. The slightly cooler but much wetter air of a humid plain or city affects it in another. Neither is harmless, but the latter can become more deceptive because the temperature number by itself may not fully express the burden. The atmosphere's hidden content, its moisture, becomes a controlling factor. The heat wave therefore changes in character as the air mass gathers humidity. What began in the outer atmosphere as a stable, continental scale pattern now becomes a more intimate environmental force. It presses against the skin, slows the body's cooling, and turns ordinary movement into effort. The science remains rooted in fluid motion, radiation, evaporation, and plant-water exchange. But the experience it creates is immediate and physical. Warmth enters the day from above, yet moisture transforms what that warmth can do. Across the United States, this combination is one reason a prolonged heat event can become far more dangerous than the numbers first suggest. The air itself acquires weight in practical terms. It becomes less able to receive more moisture, less helpful in carrying heat away from living bodies, and more effective at preserving warmth near the ground. Under such an air mass, the margin between coping and distress narrows. The event is still taking shape in the environment around people before it reaches the built surfaces of cities or the internal systems of the body, but the transformation is already underway. The heat has entered the air as temperature. It now deepens through moisture. After the broad pressure pattern settles and after the air mass grows hot and moist, the next region is time itself within a single day, especially the hours after sunset when the land and air are expected to release what they stored. In many climates, night is the interval of partial recovery. Sunlight disappears, the surface stops gaining direct solar energy, and the ground begins to lose heat upward. Air near the surface often cools with it. Walls, roads, fields, and roofs slowly give back the warmth they absorbed during the day. Human bodies also gain a chance to reduce their own accumulated heat load. Rest becomes possible not only because activity slows, but because the environment becomes less demanding. When a heat wave turns more dangerous, one of the clearest signs is that this nightly recovery weakens or fails. The night remains warm. Sometimes it remains unusually warm until dawn. The event then changes from a sequence of hot afternoons into a nearly continuous exposure. Nighttime cooling depends on several physical conditions working together. The most important is the loss of heat from the surface by radiation. Everything warm emits infrared energy. After sunset, the ground continues to radiate upward toward the sky. If the sky is relatively clear and the air is not too humid, this process can be efficient. Temperatures near the surface then fall, sometimes quickly during the first part of the night. Wind, cloud cover, moisture, soil condition, and local terrain all affect how much cooling occurs. A calm, dry inland night can cool substantially. A humid night with lingering cloud and stagnant air may cool very little. During a severe heat event, several of the conditions that normally favour cooling are reduced at the same time. The atmosphere above remains warm. Water vapour stays abundant. Winds may be light. The surface begins the evening already loaded with stored heat. The result is not complete stillness in a scientific sense, but a practical stillness in which relief does not arrive. Warm nights matter because heat is cumulative. The body, the built environment, and the natural landscape all carry thermal memory from one day into the next. A hot day followed by a cool night allows part of that memory to be erased. Soil loses heat, buildings cool, surface air freshens. The body can lower skin temperature, reduce sweating, and restore fluid balance more effectively. A hot day followed by a warm night leaves much of that memory in place. The next morning begins from a higher starting point. By midday, temperatures may reach dangerous levels sooner than they did the day before. By evening, the burden has deepened again. After several such cycles, the stress is no longer tied only to the peak heat of the afternoon. It is woven through the entire daily rhythm. The importance of warm nights is well established in heat health research. Minimum temperatures, the lowest temperatures reached before sunrise, are a major indicator of risk. When overnight lows remain elevated, rates of illness and death can rise because people receive too little environmental relief. The effect is especially pronounced in places where many homes lack effective cooling, or where people cannot afford to use it consistently. Yet the physical basis comes before the social consequences. The night itself has changed its function. It is no longer a cooling interval. It has become an extension of the event. Humidity plays an important part in this failure of nighttime recovery. Moist air slows evaporative cooling from skin, but it also affects how the lower atmosphere handles outgoing infrared radiation. Water vapour absorbs and re-emits some of the heat leaving the surface. This does not create the heat wave by itself, but it makes nocturnal cooling less effective. In effect, the lower atmosphere becomes a more active participant in retaining warmth near the ground. At the same time, if the day has been calm and sunny, roads, walls, and dry upper soils may still be releasing stored heat well after dark, where the surface is dense, dark, or dry. It often stores more daytime energy and releases it gradually through the night. Even grassland and open soil can remain warm when the daytime heating's been prolonged and the air above remains stable. Clouds can complicate the picture. Thick cloud during the day can reduce solar heating, but partial cloud or high cloud at night can act like an insulating layer, limiting how effectively the surface radiates heat away. During some heat events, skies stay mostly clear, and humidity alone is enough to weaken cooling. In others, a thin veil of cloud further narrows the path to relief. The specific combination differs across regions, but the outcome can look similar on the thermometer. The temperature falls only slightly after sunset, stalls around midnight, and remains abnormally high through the early morning hours. For living organisms, these warm nights alter basic function. Plants continue to respire at night, using some of the energy they gained during the day. If nighttime temperatures remain high, their metabolic cost can increase. Soils also respond. Microbial activity may stay elevated. Water loss from the land can continue. Streams and shallow water bodies may retain added warmth. Wildlife that normally becomes active in cooler night air may face reduced refuge from daytime heat. The night, which usually resets part of the ecological balance, instead prolongs the strain. For the human body, the difference between a cooling night and a warm one is profound even before illness appears. Skin remains warmer. Sweat loss may continue longer. Sleep becomes shallower and more fragmented because thermal comfort is reduced. The heart may continue working harder to move heat toward the skin. Fluid replacement may remain incomplete. A person can wake already tired, already slightly dehydrated, already carrying forward part of the previous day's heat burden. These effects can occur even in healthy people, and they become more serious in older adults, infants, those with chronic illness, and those whose homes retain heat strongly after sunset. The atmosphere at night therefore reveals something important about the event. A heat wave becomes more dangerous not only when daytime highs climb, but when the low point of the daily cycle rises as well. The curve of temperature over 24 hours changes shape. The descent after sunset becomes too shallow. The hours of recovery shrink. The body and the land remain within a narrower band of elevated heat for much longer. At the scale of experience, this is often when people begin to feel that the event has changed character. The day is difficult, but the night is no longer merciful. The usual promise of darkness has been altered. In this third region, nothing dramatic needs to happen in the sky. There is no visible announcement. The shift is measured in retained warmth, in weakened radiative loss, in humid air that resist cooling, and in surfaces that continue to release stored energy long after the sun is gone. Yet this quiet failure of the nightly cycle is one of the clearest markers of escalating danger. It means the atmosphere is no longer delivering heat in pulses separated by relief. It is delivering continuity. The heat remains present across the full span of day and night, and with each reduced cooldown, the event settles more deeply into bodies, buildings, and the land itself. After the broad atmosphere establishes the heat, and after the moist air mass and warm nights remove easy relief, the next region is the ground-level map of the country, where risk begins to separate into distinct local forms. At this scale, the heat wave is no longer only a national pattern overhead or a general burden in the air. It becomes a patchwork of exposures shaped by place. The same atmospheric event reaches desert cities, humid river valleys, mountain basins, coastal plains, prairie towns, dense urban corridors, and rural communities. Yet its practical severity is not identical in all of them. Local climate, recent weather, land cover, elevation, infrastructure, and human acclimatization all alter how dangerous the heat becomes. A temperature that is extraordinary in one region may be familiar in another. A humid afternoon that is survivable in a place adapted to such conditions may become far more dangerous in a place where people, buildings, and public systems are not prepared for it. The ground-level region reveals that heat is always interpreted by context. Acclimatization is one of the most important ideas in this regional view. It means the gradual adjustment of the body and society to typical local conditions. People living through a long warm season often adapt to some degree through changes in sweating efficiency, cardiovascular response, daily routines, architecture, and expectations about cooling. This does not make them immune to heat, and adaptation has clear limits, but it does change the threshold at which a given air mass becomes hazardous. A city in the northern United States may experience serious stress at a temperature that would be common in the southern plains. not because the physics of heat is different there, but because the local baseline is different. Buildings may be designed for retaining warmth rather than shedding it. Many homes may lack cooling systems. Outdoor work schedules, transit systems, and health messaging may be less tuned to repeated high heat. In this sense, danger is partly relative to the environment into which the heat arrives. Recent weather matters as much as long-term climate. If a region has already been warm for days, people and infrastructure may be strained before the newest surge of heat arrives. If a hot air mass reaches an area that has recently been cool, the body and the built environment have had less chance to adjust. Soil moisture also affects local outcomes. Wet ground uses some incoming solar energy for evaporation, which can modestly limit surface warming while increasing humidity. Dry ground devotes more of that energy directly to raising temperature. A drought-stricken region can therefore heat rapidly under strong sunlight, producing sharper daytime temperatures. Yet an area with more moisture may still be more dangerous for health if humidity rises enough to weaken sweating. The regional pattern is not simple. Dryness can intensify temperature. Moisture can intensify heat stress. Different places arrive at danger by different routes. Elevation adds another layer. Mountain regions often cool more effectively at night, especially under clear skies, but valleys and basins can trap warm air under certain conditions. A high plain may feel different from a low river valley, even under the same broad pressure pattern. Coastal areas may receive some moderation from nearby water, but that benefit depends on wind direction and the strength of the regional heat event. If winds blow inland from cooler ocean waters, the coast may gain relief. If the broader pattern suppresses that marine influence or brings air from the interior toward the shore, the coast may warm sharply as well. In enclosed coastal cities with heavy development, even proximity to water does not guarantee safety. The health community increasingly studies heat through impact-based approaches rather than by temperature alone. This reflects the regional reality. A single numerical threshold cannot capture how heat affects a nation of varied landscapes and populations. A place accustomed to moderate summers may experience dangerous health effects at values that would not trigger the same level of strain elsewhere. At the same time, traditionally hot regions can still face severe danger when heat persists for unusual duration, when nights remain too warm, or when humidity rises beyond normal local experience. The regional map is therefore not a ranking of strong places and weak places. It is a map of different vulnerabilities. Agricultural regions show this clearly. Open land may appear less threatening than a dense city, but large fields offer little shade, and work there often requires prolonged exposure. Crops themselves influence the atmosphere through evapotranspiration, which can increase humidity. Irrigated zones may feel especially oppressive when high temperature and moisture combine over open land. Rural communities may also be farther from cooling centres, hospitals, and public transit. In such places, the hazard can be amplified by distance and limited services, even though the surrounding landscape seems open and spacious. Small towns and suburban belts carry their own pattern of risk. They may not have the concentrated built heat of major urban cores, yet they often depend heavily on cars, large paved parking areas, detached housing, and long utility networks. If many homes are poorly insulated against summer heat, or if power systems come under stress, large populations can face prolonged indoor exposure. The regional perspective shows that heat danger is rarely confined to the most obvious places. It spreads through different kinds of settlement in different ways. Local social conditions also shape the map. An older population, high rates of chronic illness, low income, unstable housing, and limited access to healthcare can all turn a moderate meteorological event into a severe public health event. These are not separate from geography. They are part of place. A county, a neighborhood, or a tribal community carries specific combinations of climate, infrastructure, and health burden. The heatwave arrives from the sky, but risk is assembled on the ground from these local elements. That is why neighboring areas can experience very different outcomes under nearly the same atmospheric conditions. This regional layer is also where public warnings become more difficult and more important. A national headline may describe a dangerous heat wave across the United States, but practical guidance must account for local thresholds and local patterns of harm. Heat advisories and warnings are often issued with regional criteria because forecasters know that impact depends on place. The same measured heat index, air temperature, or overnight low may not carry the same meaning everywhere. The science of the atmosphere remains universal, but the science of risk becomes local. By this point, the heat wave has changed from a broad atmospheric pattern into a mosaic of lived realities. The dome above is large, the air mass is warm and moist, and the nights have ceased to cool as they should. Now the country beneath that sky reveals its variety. Plains, coasts, mountains, deserts, farms, suburbs, and cities all receive the same event, but they translate it differently. Some places intensify heat through dryness, some through humidity, some through architecture, some through lack of adaptation, and some through the quiet accumulation of many small disadvantages. The meteorological event remains one system, yet at ground level it becomes many overlapping forms of danger. In this fourth region, the heat wave acquires local shape, and the map of risk becomes more detailed than any single number can show. Within this regional map of risk, the next region is the condition of the air itself as a substance to be breathed. Heat does not move alone. Under stagnant summer patterns, the atmosphere can also become chemically altered and physically burdened by particles. The sky may still appear bright, and the light may still fall steadily across streets, roofs, fields, and open water, yet the air can become more harmful even before it reaches the lungs. In this region, the heat wave grows more dangerous because high temperatures, strong sunlight, weak mixing, and slow-moving air allow pollution and smoke to accumulate. The result is an environment in which breathing becomes harder, especially for those with asthma, heart disease, chronic lung conditions, or advanced age. The weather event remains a heat wave, but the body encounters it not only through temperature and humidity, it also encounters it through the altered composition of the air. One of the most important features of hot, stagnant air is the formation of ground-level ozone. Ozone high in the stratosphere protects life by absorbing harmful ultraviolet radiation, but ozone near the ground is a pollutant. It forms when nitrogen oxides and volatile organic compounds react in sunlight. These precursor gases come from vehicles, power plants, industry, solvents, fuel vapors, and other sources. During hot sunny weather, the chemical reactions that create ozone often proceed more efficiently. If winds are weak and the lower atmosphere is stable, the new ozone is not quickly dispersed. It can build across metropolitan regions and travel downwind into suburban and rural areas. The danger is subtle because ozone cannot usually be seen directly, yet its effects are measurable and well documented. It irritates the airways, reduces lung function, worsens asthma, and contributes to respiratory distress. When it appears during a heat wave, the burden on the body rises through more than one pathway at once. Heat also changes how the lower atmosphere mixes. On some days, strong daytime heating can create turbulent motion near the surface, But under a persistent high-pressure system, the broader atmosphere often remains stable enough to limit deeper vertical exchange. Pollutants emitted near the ground may then remain concentrated within the lower layer where people live and breathe. At night, if cooling is weak and inversion layers form or persist, smoke and pollution can remain trapped close to the surface until morning. This means that the very conditions that keep the heat in place can also keep unhealthy air in place. The same sky that looks calm from the ground may be preventing renewal of the air below. Smoke adds another dimension. In recent years, wildfire smoke has affected large areas of North America, sometimes spreading thousands of kilometers from the fires that produce it. Smoke contains a complex mixture of gases and tiny particles, especially fine particulate matter small enough to penetrate deep into the lungs. These particles are often called fine particles because of their small diameter, small enough to bypass many of the upper airway defenses and reach the delicate surfaces where oxygen enters the blood. Under a summer heat dome, smoke can drift into an already stressed region and remain there, diluted slowly or not at all. The visible signs may be a dimmer sun, a pale orange horizon, or a whitish cast to the sky. But the deeper significance lies in what enters the body with each breath. The combination of smoke and heat is especially harmful because both place demands on the cardiovascular and respiratory systems. Heat causes the body to direct more blood toward the skin for cooling. Fine particles and ozone can inflame the airways and contribute to systemic inflammation, meaning a body-wide inflammatory response rather than one confined to a single organ. The heart and lungs then work in a more hostile environment. Breathing may become shallower, more laboured, or more frequent. People with chronic illness may experience worsening symptoms, yet even healthy individuals can notice eye irritation, throat discomfort, cough, or an unusual heaviness in the chest when air quality deteriorates during hot weather. The chemistry of summer air is also shaped by sunlight intensity and duration. Long days provide more time for ozone-forming reactions. Warm temperatures can increase emissions of some volatile compounds from vegetation, as well as from human-made sources. Urban areas with dense traffic and industry often face the greatest ozone burden, but smoke can spread the problem across regions far from its origin. A heat wave can therefore create a broad zone where both thermal stress and air quality stress rise together. In one place, the main concern may be ozone, in another it may be smoke. In many areas, the two overlap with ordinary urban pollution, creating a layered burden that no single measurement fully captures. Visibility in such air can become misleading. A hazy sky may look gentle, almost soft, especially in evening light, but softness in appearance does not mean harmlessness in composition. Fine particles scatter light, reducing contrast and making distant objects look muted. Moist air can enhance this effect because particles absorb water and grow larger, scattering more light. The atmosphere then acquires an almost sealed quality. The horizon fades, the sunlight loses sharpness. The world looks farther away even when it is not. This visual quietness often accompanies a real reduction in air quality, and under heat it signals an environment that offers less relief than it appears to offer. Natural ecosystems are affected as well. Ozone can damage plant tissue, reducing photosynthesis and stressing crops and forests. Smoke can alter the amount and quality of sunlight reaching the ground. Insects, birds, and other animals breathe the same altered air as humans, though their responses differ by species and habitat. Streams and lakes may receive additional warmth under prolonged hot conditions, while nearby vegetation copes with both high temperature and polluted air. The landscape begins to carry signs of atmospheric strain even where human industry is distant, because pollutants travel and sunlight chemistry operates across wide areas. For human behavior, degraded air quality also changes the meaning of common heat advice. During a simple heat event, people may be encouraged to seek shade, reduce exertion, and move activity to cooler parts of the day. But when ozone is high or smoke is present, time outdoors may remain risky even in early morning or after sunset. Opening windows at night may cool a room in some circumstances, yet if smoke is dense, that act can worsen indoor air quality. Thus the air itself becomes a constraint. It narrows the options for coping with the heat. In this fifth region, the heat wave shows that atmospheric danger can deepen without any change in temperature at all. The same thermometer reading can become more harmful when the air holds reactive gases and fine particles. The event that begins with pressure, sunlight, and stagnant heat now acquires a new layer through chemistry and suspended matter. Breathing becomes part of the burden. The lungs encounter ozone, smoke, and haze at the same time that the skin and circulation encounter warmth and humidity. The environment presses inward by more than one route. This is why a heat wave can quietly cross a threshold into something far more dangerous. The sky remains bright. The weather map still shows the same broad pattern, and daily life may continue outwardly unchanged. Yet the air has become harsher in substance. Heat is no longer only felt on the skin or measured in shade. It is inhaled, reaction by reaction, particle by particle, through air that stagnates, ages, and accumulates the byproducts of fire, industry, sunlight, and summer stillness. In this region, danger becomes harder to see and easier to breathe in. After the air itself becomes part of the danger, the next region is the outer skin of the city, where the built environment receives sunlight, stores heat, and returns it slowly to the air. This regional pattern is often called the urban heat island. The phrase means that cities are usually warmer than nearby rural areas, especially after sunset, because dense construction changes how energy is absorbed, stored, and released. The effect is not imaginary and not limited to the largest metropolitan centres. It appears wherever roads, rooftops, walls, parking areas, rail lines, and other artificial surfaces replace soils, grasses, wetlands, and tree cover. Under an already dangerous heat wave, this built surface layer can raise local temperatures further and reduce the little relief that might otherwise remain. In this sixth region, the heat wave does not merely pass over the city. It enters the city's material structure and becomes part of it. The main reason lies in the physical character of urban surfaces. Many common construction materials are dark, dense, and efficient at absorbing solar energy. Asphalt, tar, brick, concrete, and some roofing materials take in sunlight throughout the day and convert a large portion of that energy into heat. They often have lower reflectivity than lighter natural surfaces, which means they send less sunlight back upward. They also tend to have greater heat capacity than thin vegetation or dry upper soil, so they store more of the heat they absorb. During the hottest part of the afternoon, these materials can become much hotter than the surrounding air. Their surface temperature may rise far above the shaded air temperature reported by a weather station. This matters because a person walking beside them is not exposed only to the air. That person is also exposed to heat radiating from the ground, walls, vehicles, and nearby structures. Tree cover changes this balance, and its absence is one of the clearest features of the urban heat island. Trees provide shade, which reduces the amount of solar energy reaching the ground and nearby walls. They also cool the air through transpiration, releasing water vapor from their leaves. In neighborhoods with sparse tree cover, more sunlight reaches pavement and roofs directly, and less energy is diverted into evaporative cooling. The surface then heats more strongly. The difference can be striking from one district to another within the same city. A leafier street with permeable ground and shaded sidewalks may remain noticeably cooler than a nearby corridor dominated by dark roofs, broad roads, and parking lots. The heat wave, therefore, becomes uneven even inside one urban area because the city's surface is not uniform. Another important factor is the geometry of streets and buildings. A city is not a flat plate. It is a three-dimensional arrangement of surfaces that absorb sunlight at different angles and exchange heat with one another. Walls receive morning and afternoon sun. Glass reflects and transmits light. Narrow streets bordered by tall buildings can remain shaded for part of the day, yet they can also trap heat and reduce air movement. Once surfaces warm, they radiate energy toward one another as well as toward the open sky. In a dense urban district, the pathways for heat loss may be narrower than they are over open land. The city becomes a place where energy is exchanged repeatedly among materials before it escapes. This slows cooling and strengthens the persistence of warmth after sunset. Water movement at the surface is also changed by urban design. In natural landscapes, some rainfall soaks into soil, where water can later return to the atmosphere through evaporation and plant use. In heavily paved areas, rain is often directed quickly into drains and channels. Less water remains near the surface to support evaporative cooling. The city therefore loses one of the quiet mechanisms by which landscapes moderate heat. Dry pavement under full sun may become extremely hot because so little incoming energy is spent on evaporation. Instead, more of it raises the temperature of the surface itself. During a prolonged heat wave, when soil moisture may already be low and vegetation may be stressed, this difference becomes even more significant. The urban heat island is strongest at night, and that is one reason it is so dangerous. During the day, the temperature difference between city and countryside may vary depending on wind, cloud cover, and local land use. After sunset, when rural land often cools more efficiently, urban materials continue releasing stored heat. Roads, roofs, and walls that absorbed energy all afternoon become sources of warmth for the surrounding air. This slows the nighttime temperature drop and can keep neighborhoods several degrees warmer than nearby less developed areas. In a major heat event, where nights are already too warm across a large region, the city adds another layer of retained heat. The loss of nighttime relief becomes even more complete. Human activity contributes as well. Vehicles release heat from engines and exhaust. Air conditioning systems cool indoor spaces by moving heat outdoors, adding warmth to alleys, courtyards, and street canyons. Industrial processes, power generation, and dense use of electricity all produce waste heat. In ordinary conditions, this added heat may be modest compared with solar energy, but during a persistent heat wave it becomes part of the accumulated burden. The city is not only absorbing heat from the sun, it is also generating additional heat from its own functions. The urban surface layer therefore behaves partly like a reservoir and partly like a machine that continues feeding warmth into the local environment. The health significance of this region is profound because people do not live in average city conditions. They live on specific blocks, in specific buildings, and move through specific routes. A bus stop without shade on a broad avenue of asphalt can expose a person to much greater heat than a nearby park entrance. An upper-floor apartment beneath a dark roof can remain far warmer through the evening than a shaded ground-floor room in a greener district. Emergency response, hospital admissions, and mortality often reflect these fine-grained differences. The meteorological heat wave may be measured across a metropolitan area, but the built environment redistributes that heat into local extremes. The urban heat island also interacts with inequality. Neighbourhoods with fewer trees, more pavement, older housing, and less investment in cooling infrastructure are often warmer. This is not only a matter of comfort, it is a matter of cumulative exposure. Over many summers, and especially during prolonged events, residents of such areas face more hours of elevated heat at the surface, indoors, and overnight. The city's material pattern becomes a health pattern. Streets, roofs, and land cover help decide who receives shade, who receives trapped warmth, and who lives in a district where the night remains hotter for longer. In this sixth region, the heatwave becomes embedded in concrete, asphalt, brick, glass, and metal. The broad atmosphere still governs the event, but the city's outer surface modifies it, intensifies it, and stores it. The danger is no longer only in the hot air overhead or the humid mass flowing across the country. It is now in the street itself, in the roof line, in the pavement underfoot, and in the hard surfaces that collect sunlight and hold it well into darkness. The urban heat island makes the city a thermal landscape of its own, one that can raise the risk of illness and exhaustion even when the official temperature appears unchanged. The heat wave strikes the nation from above, but in the city it acquires a second body, built from human materials, and that body remains warm long after the sun goes down. Within the city's heated surface, the next region narrows from the broad urban skin to the specific exposed structures that shape daily movement through modern life. Streets, roofs, parking areas, rail platforms, vehicles, loading yards, bus stops, sidewalks, and transit corridors form a network of hard surfaces that people cross, wait upon, work beside, and live under. These are not passive backdrops. They are active thermal surfaces, each with its own way of absorbing sunlight, storing energy, reflecting radiation, and releasing heat back into the air. In this seventh region, the heat wave becomes immediate through contact with the ordinary architecture of movement. The danger is no longer only that the city is warm, it is that the surfaces most closely tied to daily routines are often the ones that intensify exposure the most. Roads are among the clearest examples. Asphalt is dark and effective at absorbing solar energy. Under strong summer sunlight, its surface temperature can rise far above the measured air temperature. This does not always mean the air just above it reaches the same value, but it does mean a person near the road is surrounded by more radiant heat than a thermometer in a shaded enclosure would suggest. The heat radiates upward from the road and outward from nearby vehicles. In still air, a warm layer can linger close to the surface, especially where broad roadways, concrete medians, and minimal tree cover combine. Pedestrians, cyclists, traffic officers, road crews, delivery workers, and those waiting to cross intersections all remain inside this amplified zone. A wide avenue under full sun becomes a long channel of stored heat. Sidewalks and plazas often behave in similar ways. Concrete may reflect more visible light than asphalt, but it can still store large amounts of heat and release it steadily. Light-coloured surfaces may feel less visually oppressive, yet they can still increase exposure by reflecting sunlight toward the body and nearby walls. Heat arrives not only from beneath and around, but also from reflected solar radiation striking skin, clothing, and eyes. A person crossing an open paved square at midday may be affected by direct sunlight from above, reflected light from the ground, and infrared heat from all surrounding surfaces. Shade is therefore important not simply because it removes direct sunlight, but because it interrupts this layered field of radiation. Parking lots are especially strong heat surfaces because they combine dark pavement with large open areas and little shade. They are often attached to shopping centres, workplaces, schools, hospitals, and transit facilities, which means people must cross them for ordinary tasks even during dangerous conditions. Cars left in these spaces absorb and store heat as well. Their roofs, seats, dashboards, and steering wheels can become extremely hot under sunlight. The air inside a closed vehicle warms rapidly because sunlight passes through windows, heats the interior surfaces, and is partly trapped as a longer wavelength infrared radiation. This process is sometimes described as a greenhouse effect in common language, though the precise physics differs somewhat from the atmospheric greenhouse effect. The practical result is clear. Vehicles parked in sunlight can become lethal enclosed spaces during hot weather, especially for children, older adults, and animals left inside. Yet even without enclosure, a large parking area adds to the local burden by storing heat all day and releasing it into the evening. Roofs form another crucial layer. A roof is often the part of a building that receives the most direct solar energy over the course of a summer day. Dark roofs absorb strongly. Flat roofs can become intense heat reservoirs, especially where insulation is poor or ventilation is limited. The heat stored at the roof surface can move downward into upper floors, raising indoor temperatures and increasing the demand for mechanical cooling. At the same time, the roof radiates heat back into the surrounding air, adding to the local outdoor environment. In dense district where many roofs lie close together, the whole upper surface of the neighbourhood functions like a broad warm plate. Rooftop equipment, including air conditioning units, further contributes by rejecting indoor heat outdoors. Thus, the roof is both a receiver of solar energy and a point from which additional heat is released into the urban atmosphere. Transit corridors reveal how heat exposure follows patterns of mobility. Rail platforms, bus shelters, elevated tracks, station plazas, and roadside stops are places where people may have little control over how long they remain. A platform with metal surfaces and minimal shade can become especially harsh because metal heats rapidly and can radiate warmth strongly at close range. Glass shelters may block wind while allowing sunlight in, creating hot enclosed waiting spaces unless carefully designed for ventilation and shading. Concrete platforms store daytime heat and continue releasing it long into the evening commute. In many cities, the people most dependent on public transport are also those least able to avoid exposure by shifting work hours, travelling by private vehicle, or remaining indoors. Transit heat is therefore not merely an engineering issue. It is part of the bodily experience of unequal risk. Rail lines, bridges, and industrial corridors add a material dimension that is often overlooked. Steel tracks expand with heat. Overhead lines and equipment can be stressed by sustained high temperatures. Bridge decks warm under direct sun. Freight yards, loading docks, shipping terminals, and warehouse zones often contain extensive bare pavement and metal surfaces with little tree cover. These are work environments as much as transport environments, and they place sustained heat demands on the people within them. The same material properties that shape engineering performance also shape human exposure. A hot steel railing, a blistering platform edge, a sunlit loading bay, and a heat-radiating truck trailer all become parts of one continuous thermal landscape. The arrangement of these surfaces matters as much as their composition. A single shaded street can offer relief even in a very hot district, while an unbroken sequence of broad roads, bare sidewalks, reflective glass, and exposed stops can create a route of cumulative stress. Daily life in a city is rarely spent in one place. It unfolds as a chain of transitions, A person leaves a warm apartment, crosses a hot sidewalk, waits beside traffic, boards a vehicle, walks through an exposed parking area, enters a workplace, then reverses the journey in the evening. Each segment may appear tolerable on its own, yet together they build a sustained heat load across the day. The surfaces of mobility do not simply sit in the background. They organize repeated encounters with radiant and stored heat. The scientific significance of this region lies in the difference between air temperature and experienced heat. Weather observations are essential, but they cannot fully describe the exposure created by surrounding surfaces. Radiant heat from pavement, walls, roofs, metal structures, and vehicles can raise the thermal burden well beyond what shaded air temperature alone would imply. This is why the same official conditions can feel dramatically different in a tree-lined residential street and at a treeless intersection beside 6 lanes of asphalt. The body responds to the total environment, not only to the number reported from a distant instrument. In this 7th region, the heatwave settles into the material roots of ordinary life. Streets hold sunlight, roofs gather it, parking lots spread it across open ground, vehicles trap it, transit spaces delay relief. The city's mobility network, meant to carry people efficiently from one place to another, becomes under prolonged heat a network of repeated exposure. The wave of heat that began in the atmosphere now passes through the surfaces people touch, cross, wait beside, and move under. It becomes embedded in routine. The danger lies not only in exceptional places but in ordinary corridors, where the hard geometry of modern infrastructure turns movement itself into part of the burden. After the heat settles into streets, roofs, vehicles, and transit corridors, the next region moves inside the built shell itself, into rooms, hallways, stairwells, attics, upper floors, and enclosed workplaces where heat is not always visible, but can remain for long periods. A building is often imagined as protection from weather, and in many conditions it is. Walls block wind, roofs stop rain, windows control light. Yet under prolonged summer heat, especially when nights stay warm and exterior surfaces have stored large amounts of energy, buildings can change from shelter into reservoirs. They receive heat through roofs, walls, windows, ducts, and warm outdoor air, then release it slowly into indoor space. In this 8th region, the heat wave becomes trapped. It enters the hidden thermal life of structures and remains there, pressing on people long after they have stepped out of the sun. A building warms in several ways at once. Sunlight strikes the roof and exterior walls. Some of that energy is reflected, but much is absorbed by the outer materials. Heat then conducts inward, meaning it moves through the material from the hotter outer side toward the cooler inner side. The speed depends on what the building is made of, how thick the materials are, and whether insulation is present. Insulation slows heat transfer, but many buildings are not designed equally well for prolonged summer extremes. Some are built chiefly to retain warmth in winter. Some have aging roofs, poorly sealed windows, dark upper surfaces, or inadequate ventilation. Under these conditions, a hot afternoon does not end when the sunlight fades. The building continues to pass stored heat inward through the evening and night. Windows are another major pathway. Sunlight entering through glass can warm floors, furniture, and interior walls directly. These warmed surfaces then release heat into the room. Curtains, external shading, reflective films, and the orientation of the building all influence how much solar gain occurs. But many homes and workplaces remain exposed, especially on west-facing sides where late-day sunlight can be intense. A room may therefore feel tolerable in the morning and become oppressive by late afternoon even without any change in activity. The heat is arriving through the envelope of the building, surface by surface. Ventilation can help, but only if the air outside is cooler or drier than the air inside. During a severe heat wave, that condition often fails, especially in the late afternoon and through warm nights. Opening windows may simply admit more hot air. In smoky conditions, it may also worsen indoor air quality. Mechanical ventilation systems can move air, yet moving warm air is not the same as cooling it. A fan can assist the body's cooling under some conditions by increasing evaporation from the skin, but when indoor temperatures become extremely high, especially with high humidity, fans alone may provide limited protection and can sometimes become less effective as a safety measure. Air conditioning changes the thermal balance more directly by removing heat from indoor air and transferring it outdoors, but access is uneven. Some buildings have no cooling system. Some have old or undersized units. Some households avoid using available cooling because of energy cost, noise, maintenance problems, or unreliable power. Upper floors are often the warmest parts of a building. Heat rises through natural convection, and the roof above may be the surface receiving the strongest direct sunlight over the course of the day. Attics and poorly insulated top-story rooms can therefore become especially hot. In multi-story buildings without central cooling, the difference between lower and upper levels may be significant, particularly during long heat events. Stairwells, corridors, and enclosed common spaces may also trap warm air if ventilation is poor. Residents of upper apartments may face a long nightly struggle against heat that has accumulated in the roof and walls all day. Even if the outdoor temperature falls slightly before dawn, the indoor temperature may decline much more slowly. Thermal mass plays an important role here. Heavy materials such as concrete, brick, and masonry can absorb large amounts of heat before their temperature changes substantially. This can be useful in some climates when daily temperature swings are large and nighttime cooling is strong, because the building can dampen extremes. But during a prolonged heat wave with warm nights, the same thermal mass can become a liability. The structure absorbs heat day after day and has too little opportunity to release it fully. Indoor temperatures then drift upward over successive days. The building carries memory, just as the atmosphere and the ground do. Yesterday's heat remains embedded in the walls and floors while today's heat arrives to join it. Humidity indoors adds another layer of discomfort and risk. Cooking, bathing, breathing, laundry, and infiltration of outdoor air all contribute moisture to enclosed spaces. In poorly ventilated homes, humidity can remain elevated, which reduces the body's ability to cool by sweating. The indoor environment then becomes not only warm but close and heavy. In workplaces such as warehouses, kitchens, laundries, factories, and workshops, heat-producing equipment may add still more burden. A building that lacks sunlight can still become dangerous if internal processes, poor ventilation, and hot outdoor conditions combine. The source of heat may be partly outside and partly generated within. The experience of indoor heat is often quieter than outdoor exposure, and that quietness can make it more deceptive. There is no glaring pavement, no direct sun on the face, no shimmering road surface to signal the load. Yet a room that remains several degrees too warm through day and night can steadily wear down the body. Sleep becomes poor, dehydration deepens because sweating continues. The heart and circulation receive less respite. People who are older, bedridden, living alone, or taking medications that affect fluid balance or temperature regulation may be especially vulnerable. Yet even healthy adults can accumulate strain inside overheated rooms over several days. Buildings that are assumed to offer refuge may instead preserve danger indoors, hidden behind walls. Housing quality strongly shapes this region. Newer buildings with good insulation, reflective roofs, external shading, and efficient cooling can buffer heat more effectively. Older homes with dark roofs, thin insulation, single-pane windows, poor airflow, or overcrowded conditions may trap far more warmth. Mobile homes can heat rapidly because of their materials and exposure. Informal or unstable housing may offer little thermal protection at all. The indoor geography of risk is therefore highly uneven. Two households on the same block may face very different temperatures by midnight depending on roof condition, orientation, tree shade, floor level, and cooling access. The building also connects to the wider system through energy demand. As outdoor heat rises, more cooling is used where it is available. This increases electricity consumption, which can strain power grids during prolonged events. If power fails, indoor heat can rise quickly, especially in sealed buildings designed with the assumption that mechanical cooling will always function. The structure then reveals how dependent it has become on continuous energy input. A cooled refuge can change within hours into an enclosed hot space. In this 8th region, the heat wave no longer belongs only to the outdoors. It crosses the threshold and enters the intimate climate of human shelter. Walls absorb it, roofs hold it, windows admit it, still air preserves it. Heavy materials remember it. Rooms release it slowly through the night. The building becomes a second atmosphere, smaller than the sky above the country, but often more important to immediate survival because it surrounds the resting body for so many hours. Under prolonged extreme heat, the danger inside a structure may grow quietly while the outside world appears unchanged. What was meant to provide refuge instead becomes a chamber where warmth lingers, accumulates, and waits. Inside these heated buildings and across the exposed surfaces outside them, the next region is the human work of the day, the effort of muscles, lungs, and circulation under heat. At this scale, danger is shaped not only by weather and place but by activity. A resting body produces heat as a normal result of metabolism, the chemical processes that sustain life. A working body produces more. Walking quickly, lifting, digging, climbing, carrying, harvesting, welding, roofing, paving, cooking, cleaning, loading, drilling, and repeated athletic movement all turn chemical energy into motion and into additional internal warmth. Under mild conditions, the body can usually release this extra heat through blood flow to the skin, sweating, and faster breathing. During a severe heat wave, especially one with humidity, warm nights, polluted air, and hot surfaces, the margin for safe effort narrows. In this 9th region, the heat wave becomes more dangerous because the body is no longer only receiving heat from the environment, it is generating more of its own while already struggling to cool. Physical labor changes the thermal balance immediately. Muscles are not perfectly efficient. Much of the energy they use becomes heat rather than external work. The harder the work, the greater the internal heat production. A person carrying heavy materials upstairs in hot weather may create a far larger internal heat load than someone sitting quietly in the same air. The environment remains the same, yet the risk is transformed by effort. This is why occupational heat safety focuses not only on temperature and humidity, but also on workload, clothing, rest breaks, hydration, and acclimatization. Heat illness often develops when environmental heat and metabolic heat act together faster than the body can shed them. Outdoor work brings the clearest examples. Construction crews stand above sun-heated concrete, steel, and roofing materials. Farm workers bend and lift in open fields with little shade. Delivery workers move rapidly between vehicles and doorways across pavement and parking areas. Utility crews repair lines and equipment under direct sun, sometimes wearing protective clothing that reduces airflow and evaporation. Road workers labour near asphalt that radiates intense heat upward. Emergency responders may exert themselves in heavy gear while entering already hot environments. In each case, the surroundings raise skin temperature and reduce relief, while the work itself raises internal temperature further. The body is heated from both outside and inside at once. Clothing and protective equipment can intensify the burden. Many jobs require helmets, gloves, reflective vests, thick fabrics, respirators, or chemical-resistant layers. These garments may be necessary for safety, but they can also slow heat loss by trapping warm air near the skin, reducing sweat evaporation, and adding insulation when insulation is the last thing the body needs. Dark fabrics absorb sunlight. Impermeable materials prevent moisture from escaping. A worker may sweat heavily and still fail to cool efficiently because the sweat remains trapped or evaporates too slowly. The same principle affects athletes wearing pads and uniforms, industrial workers in protective suits, and kitchen staff surrounded by ovens and hot equipment. Clothing becomes part of the local climate around the body. Indoor work is not automatically safer. Warehouses, laundries, boiler rooms, commercial kitchens, factories, workshops, and poorly cooled service areas can hold large amounts of heat. Machinery adds waste heat, hot water, steam, motors, lighting, and refrigeration equipment all alter the indoor energy balance. Air may move poorly, and humidity may remain elevated. In some settings, the building traps heat from both outside solar gain and internal production. A person working on an upper floor in a loading bay or beside industrial equipment may therefore face high heat stress without ever standing in direct sunlight. The body responds to the actual thermal environment around it, not to whether the sky is visible overhead. Exertion also increases breathing rate. This matters because hot conditions often overlap with poor air quality. A person doing heavy work inhales more air each minute than a resting person. If ozone, smoke, or dust are present, deeper and more rapid breathing draws more of those pollutants into the lungs. The combined effect can worsen respiratory strain and reduce physical performance. The heart must circulate more blood to muscles and to skin at the same time. Fluid loss rises through sweat. Salt balance begins to shift. Fatigue arrives sooner. Judgment may weaken, and recovery between efforts becomes less complete. Acclimatization changes some of these responses. Over repeated exposure to heat, the body can improve its ability to sweat, conserve salt, and stabilize circulation during exertion. This process is real and important, but it takes time and does not erase risk. Workers returning after absence, new employees, athletes at the start of a season, and people suddenly exposed to unusual heat are often at higher risk because their adaptation is incomplete. Even well-acclimatized individuals can become ill if workload is too high, rest is too short, humidity is too great, or overnight recovery is poor. Acclimatization improves resilience, but it is not armor. Pacing becomes one of the quiet determinants of safety. A heat wave makes ordinary work harder because the body spends more effort simply maintaining itself. Tasks that feel moderate in cooler weather may become heavy in extreme heat. Muscles tire sooner because circulation is shared between movement and cooling. Concentration may narrow. Small mistakes become more likely. A missed drink of water, a skipped break, a longer walk across sunlit pavement, or an hour of extra effort before relief can shift a person from manageable stress toward heat exhaustion. The progression is often gradual at first. There may be thirst, heavy sweating, flushed skin, or unusual fatigue. Yet the deeper change is that internal heat is accumulating faster than it can be lost. Sport and recreation reveal the same physiology in another form. Runners, cyclists, field athletes, children at summer practice, and people doing yard work or long hikes all generate substantial metabolic heat. Competitive settings can mask early warning signs because attention remains fixed on performance. Young healthy bodies can still be overwhelmed when humid air limits evaporation, when surfaces radiate heat upward, or when activity continues through the hottest part of the day. Fitness does not remove the laws of thermodynamics. A fit person may tolerate strain longer, but the need to dissipate internally generated heat remains absolute. There is also a social dimension to labour under heat. Many workers cannot choose slower pace, cooler hours, or immediate rest. Pay systems, production targets, delivery schedules, staffing shortages, and fear of losing income can all press effort beyond safe limits. Some people continue because the task appears urgent, because others are also continuing, or because symptoms begin quietly and are easy to dismiss. Heat risk is therefore shaped not only by biology but by obligation. The body may need pause while the day's demands continue moving. In this 9th region, the heat wave enters human purpose and motion. It attaches itself to work shifts, harvests, deliveries, repairs, commutes on foot, training sessions, and all the repeated acts by which society functions. The environment supplies the outer load. Muscles add the inner load. Clothing, equipment, humidity, polluted air, and poor recovery compress the space between effort and collapse. A hot day becomes more than a weather condition when labour continues inside it. The body must carry out its task while also defending its own temperature. Under prolonged extreme heat, that second task may become the harder one. Within the region of work and physical effort, the next region moves closer to the uneven human landscape that determines who bears the heaviest burden when heat spreads through a country. A heat wave does not meet a single population. It meets infants whose bodies regulate temperature differently, older adults whose cooling responses may be weaker, people with heart or lung disease, people taking medications that alter fluid balance or sweating, people living alone, people without stable shelter, people in crowded housing, and people whose income, mobility, or healthcare access limit their options. In this 10th region, the heat wave becomes more dangerous because exposure is not distributed equally. The weather may cover a wide area, but vulnerability is patterned by age, illness, housing, work, poverty, disability, and social isolation. The danger grows not only through physics and physiology, but through the unequal conditions in which those forces are experienced. Age is one of the clearest factors. Very young children, especially infants, have immature temperature regulation compared with healthy adults. Their bodies have a larger surface area relative to body mass. They depend on caregivers for hydration and cooling decisions, and they cannot explain rising distress clearly. Older adults often face a different set of risks. Sweat production may be reduced, thirst sensation may be blunted, circulation may respond less flexibly, and chronic illness may already place the heart, kidneys, or lungs under strain. An older person may not feel thirsty until dehydration is already advancing. A warm room that a younger adult finds uncomfortable may become dangerous for an older adult over the course of a long night. These differences do not mean that all children or all older adults are equally vulnerable, but they show that the body's ability to adapt to heat is shaped strongly by age. Chronic illness adds another layer. Cardiovascular disease can reduce the margin by which the heart handles extra demand. During heat, blood is redirected toward the skin to release warmth, and the heart must pump more effectively to support both cooling and the body's ordinary needs. If the circulatory system is already limited, this extra task can become difficult. Lung disease can make polluted or humid air more dangerous because breathing itself becomes more taxing. Diabetes can alter hydration, circulation, and nerve responses. Kidney disease affects fluid and salt handling. Mental health conditions and cognitive impairment can interfere with the recognition of symptoms or the ability to respond appropriately. Illness does not create heat, but it narrows the range of conditions under which the body can remain stable. Medications matter because many of them alter exactly the systems heat depends on. Diuretics increase fluid loss. Some blood pressure medications influence circulation and the body's response to dehydration. Certain psychiatric medications can impair sweating or temperature regulation. Some antihistamines and other drugs with anticholinergic effects reduce the body's ability to cool by decreasing sweat production. Stimulants can raise metabolic heat and strain the heart. This does not mean such medications are inappropriate or should be stopped without medical guidance. It means that heat interacts with existing treatment in ways that can raise risk. The weather outside enters the body partly through the chemistry already at work within it. Disability and limited mobility change exposure in practical ways. A person who cannot easily leave an overheated room, open windows, travel to a cooling centre, or carry water faces a different level of danger from someone who can act quickly. A person dependent on electrically powered medical equipment may face severe risk during power outages. Sensory impairment, communication barriers, and the need for assistance with daily tasks can all slow response when heat begins causing distress. In some cases, the problem is not the body's inability to cope with temperature directly, but the surrounding system's inability to deliver timely support. Housing insecurity and homelessness create some of the most severe forms of exposure. Without stable shelter, people may endure direct sun, hot pavement, poor air quality, and limited access to water or restrooms throughout the day. At night, they may remain in places that store heat strongly, such as under concrete structures, near roads, or in encampments with little airflow. Those living in temporary or overcrowded housing may also face high indoor temperatures, inadequate cooling, and limited privacy or control over windows, fans, and daily routines. Heat becomes harder to escape when every possible refuge is compromised. The body receives little true downtime. Income shapes heat risk in ways that are both direct and cumulative. Air conditioning may exist but remain unused because electricity costs are too high. Repairs to windows, roofs, insulation, or cooling systems may be delayed because they are unaffordable. Access to a private car, time away from work, medical appointments, or cooler housing may be limited. Purchasing bottled water, blackout curtains, or even lighter clothing can be difficult for households already under financial strain. These are small material differences in one sense, yet across a prolonged heat wave they accumulate into major physiological consequences. The weather may be the same across a city, but the means of resisting it are not. Social isolation is another powerful factor. A person living alone may have no one to notice confusion, fatigue, or the failure to answer a phone call. Neighbours and family often serve as an informal safety system during heat, checking on older relatives, bringing water, adjusting fans, or urging a move to a cooler place. Where those connections are absent, symptoms can progress unnoticed. Heat illness may develop slowly and quietly, especially indoors. The absence of a witness can become part of the hazard. This is one reason mortality during heat events is often shaped not only by medical frailty, but by social networks. Language barriers, distrust of authorities, and lack of access to timely information also matter. Public heat warnings, cooling center announcements, and health guidance are only useful when they are understandable, reachable, and actionable. A person who does not receive the message, cannot read it, or cannot safely act on it remains exposed even when the wider system has issued appropriate alerts. Information is part of protection, but only if it crosses the final distance into usable knowledge. Neighborhood-level inequality deepens these individual factors. Areas with less tree cover, more pavement, older housing, fewer clinics, weaker public transit, and higher baseline illness often experience greater harm during heat waves. Historical patterns of disinvestment can leave whole districts warmer and less protected than wealthier areas nearby. In such places, the same heat event touches many vulnerable conditions at once. A resident may be older, on medication, living alone in an upper-floor apartment, dependent on walking or transit, and unable to afford continuous cooling. No single factor fully explains the risk, yet together they create a steep gradient of danger. This is why public health officials often describe heat as a silent or unequal disaster. Unlike storms that destroy visible structures in a short burst, heat often harms through the interaction of many modest disadvantages. A warm night, an unrepaired air conditioner, a bus stop without shade, a missed refill of medication, a limited income, a chronic illness, and an absent family member may seem separate, but during a prolonged event they converge in one body. The hazard is cumulative, and so is the inequality. In this 10th region, the heatwave moves fully into the social body of the nation. It reveals which lives have greater margin and which have almost none. The atmosphere above remains the same broad system, yet by the time heat reaches people through housing, age, illness, medication, mobility, and income, it has become a much more selective force. It does not choose at random. It follows the lines already present in society, deepening them through temperature, humidity, and time. The science of vulnerability is therefore not separate from the science of heat. It is the point where environment meets the unequal conditions of human life, and where the event becomes far more dangerous than weather alone can explain. After the unequal map of vulnerability comes the outer surface of the human body itself, the region where heat first meets living tissue and where cooling begins or fails. Skin is not a simple covering. It is an active organ, rich with blood vessels, sweat glands, and nerve endings that constantly measure and adjust the exchange between the body and the surrounding world. In ordinary warm weather, this system works quietly. The body senses rising temperature, opens blood vessels near the skin, sends more warm blood outward, and produces sweat. As sweat evaporates, it carries heat away. Air movement can help, shade can help, cooler surroundings can help. Under a prolonged heat wave, especially one charged with humidity and warm nights, the skin's ordinary work becomes harder. In this 11th region, the danger deepens because the body's first cooling barrier is still functioning, yet the environment begins to interfere with nearly every part of that function. The process starts with perception. Nerve receptors in the skin detect warmth from the surrounding air, from sunlight, from hot surfaces, and from the body's own rising temperature. Signals travel inward to the brain, especially to regions that regulate temperature balance. The response is not conscious in its basic form. It belongs to the autonomic nervous system, the part of physiology that controls processes such as heart rate, blood vessel width, and sweating without deliberate command. As heat exposure increases, small arteries and tiny vessels near the skin widen. This is called vasodilation, meaning the opening of blood vessels. more blood is directed toward the surface, where heat can be lost to the environment by radiation, conduction, convection, and evaporation. The word choices are technical, but the pattern is simple. The body brings warmth from its core outward, hoping the outer world will accept it. Whether the outer world accepts that heat depends on physical conditions. If surrounding air is cooler than the skin, heat can pass outward by convection and radiation. Convection means moving air carries heat away. Radiation means the body emits infrared energy toward cooler surroundings. If the air is still, hot, and close in temperature to the skin, those two pathways become less effective. The body then relies increasingly on sweat. Sweat glands release fluid onto the skin surface. That fluid is mostly water, mixed with salts and small amounts of other substances. Its purpose is not merely to wet the skin, its value lies in what happens next. If the water evaporates, it absorbs energy from the skin and cools the body. Evaporation is one of the most powerful and elegant forms of biological cooling, but it depends entirely on the atmosphere's willingness to receive more moisture. In dry air, sweat can evaporate quickly. In humid air, the space for additional water vapor is reduced. Sweat may bead, drip, or soak clothing while doing less actual cooling. This is why a person can sweat heavily and still overheat. The body's making the correct effort, but the environment is blocking the result. The skin becomes wet, yet the internal temperature may continue rising because evaporation, not sweat production alone, is what carries away heat. This distinction matters greatly during dangerous summer conditions across much of the United States. High humidity changes the meaning of skin moisture. A dry forehead in dry heat may indicate that sweat is evaporating so quickly it is barely seen. A soaked shirt in humid heat may indicate that large amounts of sweat are being produced but not providing the expected relief. The body then faces a double burden. It loses water and salts, yet gains less cooling from the loss. The cost rises while the benefit falls. Clothing changes this surface exchange further. Fabric can protect the skin from direct sunlight and reduce heat gain from radiation, but it can also trap warm air and moisture near the body. Tight or impermeable materials slow evaporation. Dark fabrics absorb more solar energy. Protective gear may add thickness and reduce airflow. The microclimate between skin and clothing then becomes warmer and wetter than the surrounding air, and the body must push harder to maintain cooling. Even loose clothing can become heavy with sweat in humid conditions, reducing comfort and limiting evaporation. The skin's cooling machinery is thus always operating in partnership with what covers it. Direct sunlight adds another layer to this outer body region. Sunlight warms the skin by radiation even when air temperature alone might seem manageable. Dark surfaces nearby may reflect or emit additional heat toward exposed arms, face, and legs. A person walking beside asphalt or concrete under strong sun receives energy from above, from the sides, and from below. The skin does not distinguish whether heat comes from sunlight, hot air, or radiant pavement. It responds to all of it through the same basic pathways of increased blood flow and sweat production. Yet the greater the incoming heat, the more aggressively these systems must work. The skin itself has limits. Sweat glands can produce large volumes of fluid, but prolonged sweating depletes body water and electrolytes, especially sodium. Blood flow to the skin can increase greatly, but that requires the heart and circulation to support the shift. If dehydration develops, blood volume falls, and the body may struggle to maintain both cooling and blood pressure. The outer cooling system then begins to compromise the inner circulation. This tension does not fully appear at the skin surface. but the first signs are often there. The skin may become very wet, very flushed, or in later stages sometimes strangely dry if sweating fails. Cramps may appear as salts, and fluids shift. Lightheadedness may follow as blood pressure becomes harder to sustain. Warm nights make this region even more important because the skin continues working after sunset. If indoor air remains hot and humid, the body cannot reduce its cooling effort. Sweat continues. Blood vessels remain open near the surface. Bedding, still air, and close rooms may trap heat against the skin. Sleep becomes restless because the body is still engaged in thermoregulation instead of true recovery. Over hours, small unresolved losses of water and salt accumulate. The next day begins not from balance but from partial depletion. Individual differences shape this surface process. Older adults may sweat less efficiently. Some medications reduce sweat production. Certain skin conditions or nerve disorders can alter heat sensing or sweating patterns. Children may produce and distribute heat differently from adults. Acclimatized individuals often begin sweating earlier and more effectively, which improves heat loss. But even this adaptation depends on adequate hydration and an environment that still allows evaporation to occur. When humidity becomes too high or heat too persistent, even a well-adjusted skin response may no longer be enough. The surface of the body is therefore both a shield and a point of vulnerability. It is where the body tries hardest to negotiate with the environment. Blood is brought outward, sweat is offered to the air, nerves monitor change and trigger response. Yet under extreme conditions, the surrounding atmosphere becomes less cooperative. Hot air reduces convective relief. Hot surfaces add radiant load. Humid air rejects moisture. Clothing traps heat. Still nights deny recovery. The skin continues its quiet labor, but the physics of the outside world begins to overmatch the physics of biological cooling. In this 11th region, the heat wave narrows to the thin boundary where a living body meets the air. The broad dome in the sky, the humid air mass, the warm city, the heated building, the working day, and the unequal map of vulnerability all now press upon this outer membrane. The skin responds exactly as it is designed to respond, with expanded vessels and flowing sweat. But design alone does not guarantee success. Cooling is a partnership between body and environment, and during dangerous heat that partnership starts to fail at the surface first. The body offers heat outward, yet the world outside accepts less and less of it. Beneath the skin and its struggling effort to release heat, the next region is the moving river within the body, the circulation of blood and the shifting balance of water and dissolved salts. This is where cooling becomes costly. To lose heat at the surface, the body must send warm blood outward. To make sweat, it must spend water drawn from its own internal reserves. During a prolonged heat wave, especially one marked by humidity, warm nights, physical effort, and poor indoor relief, this internal transport system works harder for longer than it is meant to do in ordinary conditions. In this 12th region, the danger deepens because the body's attempt to defend itself against heat begins to strain the heart, alter blood volume, and disturb the balance of fluids that every cell depends on. Blood serves many purposes at once. It carries oxygen from the lungs, nutrients from digestion, hormones from glands, and wastes toward the organs that remove them. During heat exposure, it is also used as a cooling medium. Warm blood from the body's core is directed toward vessels near the skin, where some of that heat can be transferred outward. This shift is effective only if the heart can keep pumping strongly enough to serve both the skin and the deeper organs. The challenge is immediate. When skin blood flow increases, resistance in the circulation changes. To maintain pressure and deliver enough oxygen to tissues, the heart often beats faster and works harder. In healthy individuals, this response can be sustained for a time, but it is still a burden. In older adults or in those with cardiovascular disease, the extra demand may narrow the margin of safety. The longer the heat persists, the more important body water becomes. Sweat is produced from fluid drawn ultimately from the bloodstream and from the body's broader water stores. Heavy sweating can remove large amounts of water over the course of a day, especially during labor or exercise. If intake does not keep pace with loss, total body water declines. At first, the change may be modest, but even modest dehydration affects circulation. Blood plasma, the liquid portion of blood, becomes reduced. The blood grows relatively more concentrated. The body can compensate by shifting water from other compartments and by conserving fluid through the kidneys, but these responses have limits. When volume falls, the heart must work harder to maintain output, and the delivery of blood to skin, muscles, brain, and internal organs becomes more difficult to balance. Salt balance changes alongside water balance. Sweat contains sodium and chloride as well as smaller amounts of other electrolytes, meaning minerals dissolved in body fluids that help control nerve signals, muscle contraction, and the movement of water across cell membranes. The body can adjust to repeated heat exposure by conserving salt more effectively in sweat, which is one part of acclimatization. Even so, during long periods of heavy sweating, significant sodium loss can occur. If a person replaces only water in very large amounts while sodium losses continue, the concentration of sodium in the blood can become too low. This condition, called hyponatremia, is less common than dehydration in heat illness, but it is a real risk in certain settings, especially endurance activity and prolonged sweating combined with inappropriate fluid replacement. More often, people lose both water and salt, and the body struggles to preserve enough of each to sustain normal circulation and muscle function. The brain monitors these changes through several linked systems. Rising salt concentration and falling blood volume stimulate thirst, encouraging fluid intake. Hormones such as vasopressin help the kidneys conserve water. Other hormonal systems act to preserve blood pressure and sodium balance. These responses are sophisticated and usually effective, but they depend on access to water, the ability to drink, intact kidney function, and time. During an intense heat event, especially for someone working outdoors, resting poorly at night, or living in an overheated building, the losses can outpace the corrections. Thirst may arrive late, fatigue may blunt the impulse to drink, nausea may reduce intake. Older adults may feel less thirst than younger adults even as dehydration progresses. The body's protective signals are useful, but they are not infallible. Circulatory strain affects the heart in several ways. Faster heart rate is one of the first responses to heat and dehydration. By beating more quickly, the heart tries to compensate for reduced filling and for the need to direct blood both to the skin and to essential organs. At the same time, peripheral blood vessels remain widened to support cooling. This can make standing more difficult because blood pools more easily in the lower body. A person may feel dizzy or faint, especially after sudden kang-kang. Lightheadedness in the heat often reflects this challenge of maintaining blood pressure while the circulation is already stretched between competing demands. If fluid losses deepen, the heart may no longer sustain adequate output without significant strain. The kidneys are central to this region because they regulate water, salt, and waste removal. When blood volume falls, kidney blood flow may be reduced as the body attempts to preserve circulation to other critical organs and maintain pressure. The kidneys respond by conserving water and concentrating urine, This is useful at first, but prolonged reduction in kidney perfusion, meaning blood delivery, can contribute to acute kidney injury, especially when dehydration is severe or when medications and chronic disease are already present. Workers exposed to repeated heat stress have shown patterns of kidney strain in some settings, and hospitals often see rises in dehydration-related kidney problems during major heat events. The kidney is therefore both a regulator and a vulnerable target. Heat also changes the behavior of the blood itself. As plasma volume falls, the blood becomes relatively thicker, and this can influence circulation and clotting tendency, although the degree varies by individual and condition. In people with cardiovascular disease, this concentration, combined with increased heart rate and heat stress, may help explain why hot weather is linked with higher rates of cardiac events. The precise pathways are complex and involve inflammation, vascular function, autonomic control, and existing disease. But the broad pattern is clear. Heat challenges the circulation not only by raising temperature, but by reshaping the fluid environment in which the heart must work. Muscles feel these internal shifts as well. Cramps can develop when fluid and electrolyte balance is disturbed, particularly after heavy sweating. Fatigue deepens because circulation is serving both exercise and cooling. Even mild dehydration can reduce endurance and concentration. The body begins to conserve, to slow, to signal distress through thirst, headache, weakness, and dizziness. These are not yet the deepest stages of heat illness, but they mark a circulation that is paying heavily for cooling. Warm nights make recovery from these losses harder. If sleep is poor and sweating continues in a hot room, water deficits may remain incomplete by morning. Breakfast may not replace what was lost the day before. The next round of heat begins with blood volume already reduced and salts already shifted. The heart then enters a new day of strain without having fully reset. Over several days, this cumulative effect becomes especially dangerous. The event is no longer a single exposure. It becomes a repeated withdrawal from the body's fluid reserves. In this 12th region, the heat wave moves from the body's surface into its central transport system. Blood is asked to cool and nourish at once. Water is spent to produce sweat. Sodium and other electrolytes drift from balance. Hormones act to conserve. The kidneys work to protect volume, and the heart accelerates to hold the whole system together. For a time, these adjustments can succeed, but the cost rises hour by hour. The body survives heat not by passively enduring it, but by mobilizing its circulation as an active defense. Under prolonged extreme conditions, that defense can itself become a source of strain, and the quiet losses of water and volume begin to set the stage for something more severe. Below the shifting balance of blood, water, and salts lies the next region, the body's inner temperature itself, the guarded warmth of the core. In a healthy human body, internal temperature is held within a narrow range because enzymes, membranes, nerves, and organs all work best within that limited band. The body can tolerate small changes, and it naturally rises and falls a little across the day and with activity, but only within bounds. Heat becomes a medical emergency when those bounds are crossed and the body can no longer match heat gain with heat loss. In this 13th region, the heat wave turns from severe strain into direct physiological failure. The cooling systems at the skin are overwhelmed. The circulation can no longer fully support both cooling and internal stability, and core temperature begins to rise in a self-reinforcing way. What follows is not simply discomfort made worse. It is a shift in state from thermal stress into heat illness. The body constantly produces internal heat through metabolism, even at rest. Muscles add more during movement. The environment adds heat by sunlight, hot air, radiant surfaces, and humid air that blocks evaporation. Under ordinary conditions, these inputs are balanced by losses from the skin and lungs. When the environment becomes too hot, too humid, or too persistent, the balance changes. Heat enters faster than it leaves. At first, the increase in core temperature may be slight. The body responds by sweating more, widening skin blood vessels further, increasing heart rate, and adjusting behavior through thirst and fatigue. These are protective responses. But if the mismatch continues, core temperature climbs beyond the range where normal function is easily preserved. One important stage in this progression is heat exhaustion. The term does not mean that heat has simply made the body tired. It describes a clinical state in which prolonged heat exposure, usually combined with dehydration and circulatory strain, produces weakness, heavy sweating, dizziness, headache, nausea, rapid pulse, and reduced ability to continue activity. Core temperature may be elevated, but it is not always extremely high. The defining feature is that the body is struggling yet has not fully lost its temperature control. Skin is often damp. The person may appear pale, weak, or unsteady. Thinking can become slower. The circulation is strained, and fluid deficits are often present. Without rest, cooling, and hydration, this condition can progress. The danger of heat exhaustion lies partly in how ordinary it can seem at first. Fatigue during hot weather can be dismissed as simple overwork. A headache may be blamed on missed sleep. Nausea may be taken for a minor stomach problem. Yet these symptoms often signal that the body's core temperature and circulation are drifting away from safe control. The person may still be awake, still speaking, still trying to continue. This apparent functionality can be misleading. The internal margin is shrinking. The cooling system is operating at or near its limit, and any added effort, delayed fluid intake, continued humidity, or additional time in a hot space may push the body further. As core temperature rises, the nervous system begins to suffer. The brain is especially sensitive to temperature because its cells depend on stable chemistry and steady blood flow. Even before the most severe stage is reached, people may become irritable, confused, slowed in their reactions, or poor in judgment. These changes are not merely emotional responses to discomfort. They can reflect direct physiological stress on the brain, as well as reduced circulation and dehydration. This is one reason heat illness is dangerous in solitary settings. A person may be losing the ability to assess their own condition at the same time that urgent action becomes necessary. When thermoregulation fails more completely, heat stroke can develop. Heat stroke is the most severe form of heat illness and is a true medical emergency. It is characterized by markedly elevated core temperature together with central nervous system dysfunction, meaning the brain is no longer functioning normally. Confusion, delirium, collapse, seizure, or loss of consciousness may occur. Sweating may still be present, especially in exertional heat stroke, which develops during heavy physical activity in hot conditions. This is important because older descriptions sometimes imply that heat stroke always means hot, dry skin. In reality, dry skin may occur, especially in classical heat stroke associated with prolonged environmental exposure, but sweating does not rule out the diagnosis. The key point is failure of temperature control with neurological impairment. There are broadly two patterns by which heat stroke arises, though they can overlap. Classical heat stroke tends to affect vulnerable individuals during prolonged environmental heat, especially older adults, people with chronic illness, or those trapped in very hot indoor spaces. Exertional heat stroke develops more rapidly in active individuals whose internal heat production rises sharply during work, sport, military training, or other heavy exertion in hot weather. In both cases, the essential problem is the same. Core temperature rises beyond what the body can safely manage, and organ systems begin to fail under the combined stress of heat, inflammation, and circulatory disturbance. The rise in core temperature becomes self-reinforcing because the body's protective systems themselves start to break down. Sweating may become inadequate relative to the heat load. Blood pressure may fall as dehydration worsens and vessels remain widened near the skin. Reduced blood flow to internal organs worsens metabolic stress. Cells begin to function abnormally because proteins and membranes are sensitive to high temperature. The brain's control centers may no longer coordinate an effective response. The body that has spent hours defending its temperature now loses the ability to defend it at all. This progression can happen surprisingly quickly once the threshold is crossed. A person with heat exhaustion who continues working or remains in a hot room may worsen within a short period. An athlete or laborer generating large internal heat can move from fatigue to collapse rapidly if environmental conditions prevent heat loss. The exact temperature at which this occurs varies among individuals and circumstances, and direct measurement of core temperature is not always available in everyday settings. What matters clinically is the pattern of severe overheating, together with neurological change. Altered mental status is one of the clearest warning signs that the problem has moved beyond simple heat strain. At the tissue level, rising core temperature destabilizes normal biochemistry. Enzymes work less reliably. Membranes become more permeable. Inflammatory pathways are activated. The gut barrier may become more permeable, allowing substances normally contained within the intestine to enter the bloodstream and intensify systemic inflammation. Blood clotting can become abnormal. Muscles may break down, especially after extreme exertion, releasing contents that further burden the kidneys. These deeper consequences belong partly to the next inner region, but they begin here, at the stage where uncontrolled heat turns the body's chemistry against itself. What makes this 13th region so grave is that the change is no longer primarily external. The same sky, the same hot room, the same city pavement may surround many people, yet in the person approaching heat stroke the decisive crisis is now internal. The body has ceased to maintain the narrow thermal order on which all organ function depends. The core, which should remain carefully regulated, is warming beyond its safe design. The signs may first appear as headache, dizziness, weakness, nausea, or unusual fatigue. Then speech may slow, judgment may blur, posture may fail, and collapse may follow. The threshold between strain and catastrophe is crossed not by drama in the weather, but by loss of control inside the body. In this 13th region, the heat wave becomes something far more dangerous because temperature is no longer just around the body. It is now rising within it. The skin has worked, the heart has strained, the blood has shifted, the water has been spent, and still the heat continues to accumulate. Once core temperature climbs beyond the body's ability to contain it, the event becomes a medical emergency of the deepest kind. The environment has finally pressed through every outer defense and reached the inner fire that life must keep in balance. Deeper than the rising core temperature lies the next region, where prolonged overheating begins to alter the organs themselves. The body is not built as a set of isolated parts. Its organs depend on one another through blood flow, oxygen delivery, fluid balance, nerve signaling, and chemical stability. When core temperature rises too far and circulation is forced to choose between cooling the skin and sustaining internal tissues, these linked systems begin to suffer together. In this 14th region, the heat wave becomes more dangerous because it is no longer only disturbing comfort, judgment, or physical performance. It is now threatening the structure and function of organs whose work must continue without interruption for life to persist. The injury may begin subtly, but it can spread quickly, and even after immediate survival the effects may linger. The kidneys are among the first organs to show the cost of prolonged heat strain. Their task is to filter the blood, remove wastes, regulate water and salts, and help maintain the chemical stability of the body. To do this well, they require steady blood flow. During severe heat exposure, especially when dehydration has reduced blood volume, kidney perfusion may decline. The body tries to preserve circulation to the most immediately vital functions, and the kidneys respond by conserving water and concentrating urine. This is an intelligent short-term defense, but it also reveals how narrow the margin has become. If reduced blood flow persists, kidney cells can be injured. Waste products then begin to accumulate, fluid regulation worsens, and the balance of electrolytes may drift further abnormal. In hospitals, major heat events are often accompanied by rises in kidney-related illness, because dehydration and heat stress together place this organ under exceptional pressure. Muscle tissue can also be damaged by extreme heat, especially when heavy exertion is part of the story. Muscles working hard in a hot environment generate large amounts of internal heat. If circulation becomes inadequate and temperature rises too high, muscle fibers may begin to break down. This process is known as rhabdomyolysis, a technical term for the release of muscle cell contents into the bloodstream after injury. The meaning is simple even if the word is not. The body's own working tissues begin to disintegrate under the combined stress of heat, effort, and failing circulation. Substances released from damaged muscle, including myoglobin, can further burden the kidneys and worsen the risk of acute kidney injury. What begins as muscular effort under heat thus becomes a deeper organ crisis, one system amplifying damage in another. The liver is also vulnerable. It helps process nutrients, toxins, and metabolic byproducts, and it contributes to the regulation of many essential chemical pathways. Severe overheating and reduced circulation can injure liver cells, causing measurable abnormalities in blood tests and sometimes more serious dysfunction. The liver's vulnerability shows that heat illness is not only a matter of temperature, but of oxygen and perfusion. Organs do not fail simply because they are hot. They fail because heat changes cellular chemistry while circulation becomes less able to deliver what cells need and remove what they produce. High temperature and reduced blood flow are a dangerous combination. Together, they push cells toward injury from more than one direction at once. The brain, already affected in heat stroke by confusion and altered consciousness, remains one of the most sensitive organs in this deeper region. Brain cells depend on precise temperature control, steady blood flow, and tight chemical regulation. When core temperature rises and the blood-brain balance is disturbed, neurons may function abnormally. This can appear outwardly as delirium, agitation, slowed response, seizure, or coma. But even beyond these obvious clinical signs, there may be direct cellular stress from heat and inflammation. Swelling can develop. The normal signaling that coordinates movement, memory, and awareness may be disrupted. Some people recover fully after rapid treatment. Others may be left with lingering neurological effects, especially when severe heat stroke has been prolonged. The brain reveals with particular clarity that heat is not merely exhausting. At its deepest level, it is destructive. The heart is both a driver of the body's defense and a target of its failure. Throughout heat exposure, the heart beats faster to support cooling and maintain blood pressure. If dehydration deepens, the blood volume falls and the workload rises further. For people with existing cardiovascular disease, This added demand can trigger chest pain, arrhythmias, or worsening heart failure. Even without prior disease, severe heat illness can alter the electrical stability of the heart because electrolyte imbalance, inflammation, and circulatory stress affect how the heart muscle conducts impulses. The organ that has laboured to preserve internal order may begin to lose its own rhythm. This is one reason extreme heat is associated with increased rates of sudden medical deterioration, especially among those whose hearts already carry hidden fragility. The lungs occupy a different but related place in this inner crisis. Hot conditions alone do not injure the lungs in the same direct way as smoke or infection, yet the lungs are deeply involved in the body's response to heat. Breathing may become faster during exertion, distress, or acidosis, a condition in which the body's chemistry becomes more acidic than normal because of metabolic disruption. If smoke, ozone, or particulate pollution are also present, the lungs bear a compounded burden. In severe heat illness, inflammation can spread throughout the body and affect the permeability of blood vessels, sometimes contributing to fluid shift that make breathing harder. The lungs then become not merely the route of oxygen entry, but another organ coping with systemic stress. A person who is severely overheated may breathe rapidly, not only from discomfort, but because multiple internal systems are beginning to fail. The intestine, often overlooked in ordinary descriptions of heat illness, plays an important role in deeper organ stress. Under intense heat and reduced blood flow, the gut lining can become more permeable. The barrier that normally keeps intestinal contents separate from the bloodstream begins to weaken. This allows bacterial products and other substances to cross into the circulation, which can intensify inflammation throughout the body. Heat stroke is therefore not only a problem of excess temperature, it can become a whole-body inflammatory state in which the immune system is activated, and tissues far from the skin are drawn into the crisis. The gut, the liver, the circulation, and the immune response then become part of one connected process of injury. Blood clotting can also be disrupted. In severe heat stroke, the normal balance between clot formation and clot breakdown may fail. Tiny clots can form inappropriately within small vessels, while clotting factors are also consumed, producing a dangerous instability. This complication is part of the reason heat stroke can resemble other forms of systemic collapse. The body is no longer suffering from warmth alone. It is entering a condition where inflammation, coagulation, cellular injury, and circulatory failure interact across multiple organs at once. Modern medical care can interrupt this progression if treatment begins rapidly, but the underlying biology is grave. These organ effects help explain why surviving a severe heat event is not always the end of the story. Some people who recover from acute heat illness later show ongoing kidney problems, neurological difficulties, or reduced tolerance for future heat. Research continues into the long-term consequences, and uncertainty remains about how often lasting injury follows different levels of severity. Observations indicate that the risk is real, especially after true heat stroke, though not every survivor experiences permanent damage. What is clear is that extreme overheating is capable of leaving marks deeper than temporary fatigue or dehydration. Organs remember major insults, just as cities and buildings remember repeated heat in their materials. In this 14th region, the heat wave reaches a level at which the body's internal cooperation begins to fracture. The kidneys conserve until they cannot, muscles break down under strain, the liver falters, the heart labours and may lose stability, the lungs struggle within a disturbed internal chemistry, the gut barrier weakens, inflammation spreads, clotting becomes disordered. Each organ both suffers its own injury and contributes to the burden on the others. The system that usually functions as one integrated whole begins to come apart under heat, lack of water, reduced blood flow, and rising internal temperature. What began under a broad summer sky has now entered the deepest chemistry of human life, and in these organs the hidden seriousness of extreme heat becomes fully visible. At the innermost region of this heat event lies the quietest and most dangerous transformation, the point at which the body's failing systems begin to alter awareness, behavior, and the final margins of survival. By now, the path inward has moved from the continental atmosphere to moist air, from warm nights to local exposure, from polluted skies to city surfaces, from buildings to labor, from unequal vulnerability to skin, blood, core temperature, and organs. In this last section, all of those outer layers converge inside the most fragile human functions. The heatwave becomes far more dangerous because its deepest failures are often not loud. They emerge as confusion, delayed reaction, poor judgment, weakness, silence, and collapse. What is most life-threatening may not announce itself dramatically at first. It may appear as a person sitting too long in a hot room, speaking less clearly than usual, walking more slowly across a parking lot, forgetting to drink, missing a bus stop, failing to recognize danger, or losing the strength to act in time. The brain is central to this final stage because it governs both physical regulation and conscious response. Earlier, it coordinates sweating, thirst, and circulation. Later, under severe heat stress, it begins to lose the ability to interpret the body's condition correctly or to produce useful action. Confusion is one of the most important signs for this reason. It means the threat has moved beyond simple discomfort into altered brain function. A person may insist on continuing to work, may remove protective clothing at the wrong time, may refuse water, may speak incoherently, or may become strangely calm while internal temperature rises. This calmness can be deceptive. Heat does not always drive the body into visible panic. Sometimes it produces a narrowing of thought, a slowing of response, and a fading of judgment. The body becomes less able to save itself at the very moment self-protection is most needed. This loss of judgment is one reason heat can kill quietly indoors. A person alone in an overheated apartment may feel exhausted and lie down, expecting rest to help. If the room remains hot and humid, cooling does not occur. Dehydration may deepen through continued sweating. Blood pressure may fall when standing, making it harder to reach water or a cooler place. The person may become progressively weaker and less clear-headed. The room is still. The building stands unchanged. No visible disaster is occurring, yet within that stillness, circulation, thermoregulation, and brain function are slipping together. The failure is hidden because it resembles fatigue until it becomes incapacity. Collapse in heat is often the last visible point in a much longer process. Before a person falls, many smaller failures may already have accumulated. Fluid may have been lost over many hours. Sleep may have been poor for several nights. Medication may have blunted thirst or sweating. The surrounding neighborhood may have offered little shade and no easy refuge. A power outage may have raised indoor temperatures. Work may have continued because wages were needed. None of these factors alone guarantees catastrophe. Together they erode reserve. By the time collapse occurs, the body may have been operating near its limit for days. When consciousness changes under heat, danger rises sharply because basic protective behaviors begin to fail. Drinking water requires recognition of thirst, access, and the will to act. Seeking shade or cooling requires spatial judgment and physical coordination. Calling for help requires cognition, speech, and sometimes access to communication. Even maintaining posture depends on circulation and nervous system function remaining intact. Heat undermines all of these at once. A person may stumble not simply from tired muscles, but from falling blood pressure, worsening dehydration, and a brain that is no longer processing balance normally. Speech may become slow because neurons are stressed. Silence may not mean comfort, it may mean withdrawal, confusion, or the onset of collapse. This inward failure can also be socially invisible. In crowded cities, many people in distress are seen only briefly by strangers, on public transport, in waiting rooms, in parking lots, at job sites, and in apartment buildings. Early heat illness may look like ordinary weariness. Someone sitting motionless in shade may seem to be resting. Someone who is confused may be mistaken for intoxicated or simply distracted. Someone who does not answer the door may be assumed to be asleep. Heat takes advantage of this ambiguity, because it often leaves structures standing and landscapes apparently intact. It can pass beneath attention until medical crisis is advanced. The quietest failures are dangerous in part because they do not immediately trigger the same social alarm as fire, flood, or violent storm. The body's final descent in severe heat often involves a narrowing of circulation and consciousness together. Blood volume has fallen, the heart is strained, skin may still be hot, and sweating may persist or begin to fail. The brain receives less stable support. Internal chemistry becomes more disordered as electrolytes shift, inflammation spreads, and organ injury worsens. The person may feel detached, weak, or strangely indifferent. Then posture gives way. Collapse can happen while walking, lifting, standing in line, sitting in a hot room, or trying to rise from bed, once on the ground. The body is no longer generating as much internal heat from effort, but that does not mean safety is returned. If core temperature is already dangerously high, collapse may be only the visible beginning of terminal failure unless rapid cooling and emergency care follow. At the population scale, these quiet failures explain why heat mortality is often underestimated. Death may be recorded under heart disease, kidney failure, respiratory illness, or another immediate cause that was worsened by heat rather than labelled as heat alone. Many deaths occur among people whose existing conditions are pushed beyond tolerance by prolonged exposure. The heat wave does not always act as a solitary force. It acts as an amplifier, tightening every physiological limit already present. A modest reduction in sleep, a modest increase in dehydration, a modest decline in circulation, and a modest burden of chronic disease may together become fatal under extreme heat. The final outcome may therefore appear medically complex while still being deeply rooted in the weather event that set the process in motion. There is also a temporal quietness to these failures. They often happen after multiple days of exposure, after the drama of the first warning headlines has faded into routine. People adapt their expectations. The hot day begins to feel normal because it has repeated so often. Yet repetition is part of the danger. The body is not a machine that resets completely each night, especially when nights remain warm. The innermost risk is cumulative. It grows in small increments of unrecovered stress until the remaining margin disappears. This is the deepest truth of the title's warning. A heat wave turns into something far more dangerous when it stops being merely an outdoor condition and becomes a total inward burden. It enters breath, buildings, work, skin, circulation, organs, and finally awareness itself. At the last stage, the gravest signs may be quiet ones: a missed step, a delayed answer, a dry mouth ignored, a thought that does not fully form, a room that remains too warm until morning. a body that can no longer recognize how near it is to its limit. Heat does not need violence to become lethal. It needs persistence, humidity, retained warmth, unequal exposure, and the gradual exhaustion of the body's ability to compensate. In that way, the final failures arrive with little spectacle. They are the most inward consequences of a broad atmospheric event, and they are often the hardest to see before it is too late. The heat wave now comes to rest at the smallest scale, not in the sky above the continent and not in the streets or buildings alone, but in the body lying still after a long day and a long night. The broad dome of high pressure remains an atmospheric fact. The humid air remains a physical condition. The city, the road, the roof, the room, and the labour of the day remain part of the same chain. Yet in the quiet hours, all of that outward structure is reduced to a simpler question of balance. The body must release enough heat, keep enough water, preserve enough circulation, and hold awareness clear enough to continue. When the surrounding world is too warm for too long, that balance grows difficult to maintain. Extreme heat is often described through records, maps, and forecast numbers, and these are necessary. They show the scale of the event and its movement across the land. But the deeper meaning of heat is always intimate. It is measured in the warmth that remains in walls after sunset, in the breath drawn from heavy air, in the pulse that does not quite settle, in the skin that keeps sweating through the dark, and in the slow fatigue that accumulates when recovery fails. Heat becomes most dangerous when it is continuous, when it enters every layer of daily life and leaves too little space for the body to restore itself. So the event ends where all weather is finally experienced, in living tissue trying to remain within its narrow range of order. The atmosphere above the United States may appear calm, almost empty, under a pale summer sky, but beneath that stillness, energy continues to move through air, stone, water, skin, blood, and thought. The danger lies not in noise but in persistence. It lies in the steady refusal of the heat to let go,